Hello there, and welcome to the Science for Sleep channel. Tonight we'll explore the storms that have rolled across this planet since long before any living thing existed to watch the lightning flash. Rain born from ancient oceans, thunder echoing across empty continents, and lightning striking the bare ground of a young Earth. These quiet, powerful forces have been shaping our world for billions of years, and they are still at work tonight, somewhere out there in the dark sky above you. You've got nothing to do but rest. Let your mind grow still, your breathing slow, and your body sink gently into the quiet. If this helps you sleep, consider liking and subscribing, one sleepy soul at a time. Lightning is one of the most powerful and beautiful forces in all of nature. Every single bolt of lightning is about 5 times hotter than the surface of the sun, reaching temperatures of around 30,000 degrees Celsius in a fraction of a second. That is hard to imagine because the sun itself is already so incredibly hot that nothing on Earth could survive touching it. Yet lightning achieves that temperature in the blink of an eye, right here in our own sky. This extreme heat happens because electricity forces its way through the air very quickly, and the air resists it, creating an enormous burst of energy. The bolt itself is surprisingly thin, only about as wide as a human thumb. But the light it produces is so intense that it can be seen from many miles away, cutting across the sky like a crack in the darkness. Every time you see a flash of lightning, you are witnessing one of the most energetic events that nature can produce right above your head. A single thunderstorm carries an almost unimaginable amount of energy inside it. Scientists have calculated that a large thunderstorm can release more energy than an atomic bomb. And some of the biggest storms release far, far more than that. This energy comes from warm, moist air rising quickly into the sky, cooling down, and releasing heat as water vapor turns into water droplets and ice. That process, which sounds so gentle and simple, is actually a powerful engine that drives the entire storm. The bigger and taller the storm cloud grows, the more energy it contains. Some thunderstorm clouds reach so high into the atmosphere that their tops spread out flat like an enormous anvil, pushing against the very edge of the lower atmosphere. All of that rising air, falling rain, electricity, and wind is part of one connected system, a living, breathing machine made entirely of water, air, and energy that nature builds and destroys in just a few hours. Right now, as you read these words, there are roughly 40,000 thunderstorms happening somewhere on Earth. That number is almost impossible to picture. 40,000 separate storms, each one full of lightning, thunder, and heavy rain, all occurring at the same time across our planet. Some are forming over warm tropical oceans, feeding on the heat rising from the water below. Others are building over hot and humid land, where the afternoon sun heats the ground and pushes warm air rapidly upward. A few are passing over mountain ranges, growing taller as the mountains force the air to rise even faster. At any given moment, roughly 1/3 of Earth's surface is experiencing some kind of stormy weather. Storms are not rare events at all. They are constant, tireless, and everywhere. The clear blue sky above you is actually the exception. A quiet pause between the endless cycle of storms that have circled this planet every single day for billions of years. Every second of every day, lightning strikes the Earth approximately 100 times. That means in the time it takes you to read this paragraph, hundreds of lightning bolts have already connected the sky to the ground somewhere in the world. Some strike open fields, setting grass briefly on fire before the rain puts it out. Others hit the ocean, disappearing silently into the water. Some strike trees, splitting them open instantly with a crack that can be heard from a great distance. Tall buildings in cities are struck over and over again throughout the year, which is why they are fitted with lightning rods, metal conductors designed to safely guide the electricity down into the ground. Lightning does not choose where to strike randomly. It always follows the path of least resistance, the easiest route from sky to Earth. That path changes in milliseconds, which is why lightning bolts zigzag so unpredictably across the sky before finally finding their way down. A tornado is one of the most dramatic and awe-inspiring sights in all of nature. These spinning columns of air can reach wind speeds of over 300 miles per hour, making them faster than almost any vehicle ever built by humans. A powerful tornado can pick up an entire house, pull it off its foundation, and carry it through the air for miles before dropping it back down. It can strip the bark completely off trees, leaving them pale and bare. It can drive pieces of straw deep into wooden fences like tiny arrows. The funnel shape that we recognize so easily forms when a column of rotating air stretches down from the base of a thunderstorm cloud and touches the ground. Once it makes contact, the destruction can begin in seconds. Yet despite all this incredible power, a tornado is usually only a few hundred meters wide. A narrow, concentrated finger of spinning air that moves across the landscape, leaving a thin path of change behind it. One of the strangest and most surprising things about a hurricane is what you find at its very center. While the outer edges of a hurricane bring howling winds, torrential rain, and enormous waves, the center of the storm, called the eye, is almost completely calm. The sky above the eye is often clear, with stars visible at night and sunlight streaming down during the day. The winds drop to nearly nothing. The rain stops. Birds have been found resting inside hurricane eyes, carried along by the storm without realizing the chaos surrounding them on all sides. The eye forms because of the way air rotates around the storm. It rises along the edges, spirals inward, but then sinks gently back down in the center, creating a bubble of stillness. This calm can last for hours as the eye passes over land or sea before the other side of the storm arrives and the fierce winds return just as suddenly as they stopped. Some hurricanes grow so enormous that they can be clearly seen from space without any special equipment. Astronauts aboard space stations have described looking down at Earth and seeing a giant white spiral slowly turning in the ocean below, so large it seems to cover an entire sea. The biggest hurricanes can stretch over 1,000 kilometers from one side to the other, making them wider than many countries. From above, the spiral shape is perfect and almost beautiful, a graceful curve of clouds wrapping around a small, clear center. That beauty, however, contains some of nature's most destructive forces. The same elegant spiral that looks so peaceful from space is, at ground level, a wall of wind and water powerful enough to reshape coastlines, flood cities, and uproot forests. Seeing a hurricane from space gives a sense of its true scale. Not just a local storm, but a planetary event. A massive engine of energy spinning slowly across the face of the ocean. Inside a powerful thunderstorm, the air is constantly moving in ways that create remarkable and sometimes dangerous things. Strong updrafts, columns of air rushing rapidly upward, can lift water droplets high into the freezing upper atmosphere, where they begin to form ice. As these ice particles are tossed up and down by the storm's violent winds, they collide with each other, building up layers and growing larger with every trip through the cloud. Over time, they can grow into hailstones, balls of ice that fall from the sky when they finally become too heavy for the updrafts to hold up. Most hailstones are small, like peas or marbles, but in the most powerful storms, they can grow as large as grapefruits, weighing close to a kilogram. A hailstone that size, falling from thousands of meters in the sky, carries enough force to dent metal, shatter glass, and flatten crops in minutes. Thunder is the voice of a storm, that deep, rolling boom that follows every flash of lightning. But thunder is not simply a loud sound. It is actually a sonic boom, the same kind of explosive noise produced when something moves faster than the speed of sound. When lightning strikes, it heats the air around it almost instantly to extreme temperatures. That air expands outward at incredible speed, faster than sound, and that rapid expansion creates a shock wave. The shock wave is what we hear as thunder. If you are very close to a lightning strike, the thunder sounds like a sharp, deafening crack because the shock wave reaches you almost instantly. If the lightning is far away, the sound reaches you later and is spread out, becoming that familiar, long, low rumble rolling across the sky. The gap between the flash and the thunder tells you exactly how far away the lightning was. about 1 kilometer for every 3 seconds of silence. Jupiter, the largest planet in our solar system, has a storm that has been raging for hundreds of years without ever stopping. This storm is called the Great Red Spot, and it is so large that the entire planet Earth could fit inside it with room to spare. It appears as a huge reddish oval on Jupiter's surface, visible through even a small telescope from Earth. Scientists believe this storm has been spinning continuously since at least the 1600s, when early astronomers first noticed it. On Earth, the strongest storms last a few weeks before they weaken and disappear. But Jupiter's atmosphere is so thick, so deep, and so full of energy that this single storm has never found a reason to stop. It is a reminder that storms are not unique to our planet. They are a feature of any world with an atmosphere, and on some worlds, they can last longer than entire human civilizations. Inside a thunderstorm cloud, something invisible and extraordinary is happening. The cloud is filled with millions of tiny ice crystals and water droplets, all moving rapidly in different directions, colliding constantly with one another. These collisions create a buildup of electrical charge. Positive charges gather near the top of the cloud, and negative charges gather near the bottom. As this separation of charges grows stronger, the difference in electrical energy between the cloud and the ground below becomes enormous, reaching millions of volts. Eventually, that energy finds a way to release itself in one brilliant, violent instant, a lightning bolt. The bolt travels from cloud to ground, or sometimes from cloud to cloud, in a fraction of a second. The entire process, from the first tiny collision of ice crystals to the final blinding flash, happens invisibly and silently inside the cloud for many minutes before the lightning ever appears. The storm builds its electricity slowly and patiently, then releases it all at once. Rain that falls inside a powerful storm does not always reach the ground. This surprising fact is known as virga, and it happens when raindrops fall from the base of a cloud but pass through a layer of very dry or very warm air on the way down. As the drops fall through that dry air, they begin to evaporate, turning back into invisible water vapor before they can reach the earth below. From a distance, virga looks like thin, wispy curtains of gray hanging beneath a cloud, trailing downward and fading away before touching the ground. It is rain that almost made it. In desert regions, virga is especially common because the air near the ground is so hot and dry that even heavy rain can disappear completely before landing. A storm can release enormous amounts of water into the air above a desert and yet leave the sand below completely dry and undisturbed, as if the rain never happened at all. The largest hailstone ever officially recorded fell during a storm in the United States in the year 2010 in the state of South Dakota. It measured about 20 centimeters across, roughly the size of a volleyball, and weighed nearly a kilogram. To form a hailstone that large, a storm must have extremely powerful updrafts capable of lifting the growing ball of ice repeatedly back into the freezing upper part of the cloud before it finally falls. Each time the hailstone is lifted back up, it passes through a layer of supercooled water droplets that freeze onto its surface, adding another thin shell of ice. Scientists can cut a large hailstone in half and count the layers inside, much like counting the rings of a tree to understand how many times it traveled up and down inside the storm, before finally becoming too heavy to stay airborne and crashing down to the ground below. Tornadoes are most common in a broad stretch of land in the central United States that scientists and storm chasers have nicknamed Tornado Alley. This region includes states like Texas, Oklahoma, Kansas, and Nebraska, where the geography creates nearly perfect conditions for tornadoes to form. Warm, moist air flows north from the Gulf of Mexico and collides with cold, dry air coming south from Canada. At the same time, dry air from the Rocky Mountains slides in from the west at higher altitudes. When all three of these very different air masses meet in the same place, the result is often a powerful supercell thunderstorm, the kind that produces the most violent and long-lasting tornadoes on Earth. The flat, open landscape of the Great Plains means there are no mountains or hills to slow the storms down or disrupt the spinning air. Every spring, this region experiences dozens of tornadoes, sometimes in a single dramatic day of storms. Hurricanes spin in opposite directions depending on which side of the equator they form. In the northern hemisphere, hurricanes rotate counterclockwise, while in the southern hemisphere, they rotate clockwise. This happens because of something called the Coriolis effect, a result of the Earth spinning on its axis. As air rushes inward toward the low-pressure center of a storm, the rotation of the Earth gently deflects it to one side. In the north, this deflection curves the air to the right, creating a counterclockwise spin. In the south, the deflection curves it to the left, producing a clockwise rotation. The Coriolis effect is very subtle for small things like water draining from a bathtub, too subtle to actually affect which way your drain spins, despite the popular myth. But for something as enormous as a hurricane, spread across hundreds of kilometers of ocean, the effect is powerful enough to determine the entire rotational direction of the storm. Tropical storms are given human names to make it easier for scientists, governments, and the public to track and communicate about them. Before this system was introduced, storms were identified only by their position and date, which made it confusing when multiple storms were active at the same time. The modern naming system began in the mid-20th century, and today lists of names are prepared in advance for each storm season, alternating between male and female names in alphabetical order. Different regions of the world use different lists. Atlantic hurricanes have one set of names, Pacific typhoons have another. If a storm is particularly destructive or deadly, its name is retired from the list permanently and never used again as a mark of respect for the damage it caused. Names like Katrina, Harvey, and Maria will never be given to another storm, preserved in history as reminders of the power these events carry. Some thunderstorms produce lightning, but no rain reaches the ground at all. These are called dry thunderstorms, and they are particularly common in hot, dry regions like the American West and parts of Australia. Just like regular thunderstorms, they build tall clouds, generate electricity, and release lightning bolts. But the rain that falls from the cloud base evaporates completely before reaching the earth, just like Virga. The result is lightning striking dry ground, dry grass, and dry forests with no rain to dampen anything. Dry thunderstorms are one of the leading causes of wildfires in many parts of the world, because a single lightning strike can ignite a dry hillside and start a fire that spreads for kilometers. Firefighters in regions where dry thunderstorms are common watch the sky very carefully during summer storms, knowing that a flash of lightning with no following rain is one of the most dangerous things nature can produce. When a powerful hurricane moves toward a coastline, the most dangerous part of the storm is often not the wind. It is the storm surge. A storm surge is a massive rise in sea level caused by the storm's strong winds pushing ocean water toward the shore for hours or even days. The low atmospheric pressure at the center of the hurricane also allows the ocean surface to bulge upward slightly. Together, these effects can raise the sea level by 5, 6, or even 9 meters above normal in some extreme cases. This wall of water arrives at the coast like a slow but unstoppable flood, pushing far inland and covering everything in its path. Storm surges have historically been responsible for more deaths during hurricanes than wind, rain, or any other factor. Entire low-lying coastal communities can be submerged within minutes when a surge arrives, which is why evacuation orders before a hurricane are taken so seriously by emergency services. When you walk outside after a thunderstorm and breathe in that clean, fresh, almost electric smell in the air, you are detecting a real molecule, one that your nose is surprisingly good at noticing. That distinctive scent is caused largely by ozone, a molecule made of 3 oxygen atoms bonded together. Lightning produces ozone by breaking apart ordinary oxygen molecules in the air and allowing the individual atoms to recombine in groups of 3. Ozone has a sharp, slightly sweet smell that many people find pleasant and refreshing. Rain also releases another scent called petrichor, the earthy, warm smell that rises from soil when the first drops of rain hit dry ground after a long dry period. Together, ozone and petrichor create that unmistakable perfume of a passing storm. These scents are a gentle, invisible reminder that the storm has been here, has changed the chemistry of the air itself and has moved quietly on. Waterspouts are one of the most visually dramatic phenomena that storms can produce over the ocean. They look like tornadoes, and in many ways they are, but they form over water rather than land. Some waterspouts develop from thunderstorms above, growing downward toward the sea in the same way that land tornadoes do. Others form more gently, rising upward from the sea surface on calm days under just the right atmospheric conditions, without any severe storm above them. Waterspouts can suck up seawater, fish, and small sea creatures into their spinning column of air, and then drop them back down far from where they were picked up. There are historical accounts of fish and frogs raining down from the sky after being carried by waterspouts, which must have seemed like a miracle to people who had no way of explaining it. Waterspouts are usually weaker than land tornadoes, but they can still be dangerous to small boats and aircraft flying nearby. Dust storms are among the most dramatic weather events on Earth, and some of them travel astonishing distances across the planet. The Sahara Desert in northern Africa produces enormous clouds of fine sand and dust that are lifted high into the atmosphere by powerful winds. These particles can be carried by upper-level winds all the way across the Atlantic Ocean, a journey of thousands of kilometers before settling down over the rainforests of South America. Scientists have discovered that this Saharan dust actually contains minerals and nutrients that fertilize the Amazon rainforest, feeding the soil and helping the forest grow. In a very real sense, the desert and the jungle are connected by the invisible highway of the wind. The same storms that seem destructive and suffocating in the desert are quietly delivering a gift to forests on the other side of the world. It is one of nature's most surprising and beautiful long-distance relationships, carried entirely on the back of a storm. A thunderstorm cloud, known scientifically as a cumulonimbus, is the tallest type of cloud that forms in Earth's atmosphere. While most clouds float at relatively low or medium altitudes, a fully developed cumulonimbus can stretch from just a few hundred meters above the ground all the way up to 15 or even 18 kilometers high. That is taller than Mount Everest, the highest mountain on Earth, which reaches about 8.8 kilometers. At the very top of the cloud, the temperature is far below freezing, and the air is so thin that it is close to the conditions found at the edge of space. The top of the cloud often spreads out into a flat, wide shape that looks like a blacksmith's anvil, which is exactly what meteorologists call it, an anvil cloud. This shape forms because the rising air inside the storm hits a boundary layer in the upper atmosphere and can no longer go higher, so it spreads outward in all directions like water hitting a ceiling. Thundersnow is a rare and wonderful weather event that surprises even experienced meteorologists when it happens. It occurs when a snowstorm develops enough energy and instability to also produce lightning and thunder, the same electrical processes that happen in a regular summer thunderstorm, but taking place inside a winter snowstorm instead. Because snow absorbs and muffles sound more effectively than rain, the thunder in a thundersnow event sounds much softer and more muffled than typical thunder, almost like a low, distant rumble felt as much as heard. The lightning, however, is just as real and just as powerful as in any other storm. Thundersnow is most common near large lakes in winter, particularly around the Great Lakes in North America, where cold air passing over warmer lake water picks up heat and moisture rapidly, creating the unstable conditions needed for electrical activity inside a snowstorm. Ball lightning is one of the most mysterious and puzzling phenomena in all of weather science. It appears as a glowing, floating sphere of light, usually about the size of a grapefruit or larger, that drifts slowly through the air during or after thunderstorms. Reports of ball lightning describe it in many colors: white, yellow, orange, red, and sometimes blue. It can pass through glass windows, float through rooms, and then either fade away silently or disappear with a sudden loud pop. People have reported seeing it for centuries, from ancient sailors to modern pilots. Despite hundreds of credible eyewitness accounts, scientists still do not fully understand what ball lightning actually is or how it forms. Several theories have been proposed involving plasma, microwave radiation, and burning silicon vapors, but none has been proven completely. It remains one of the few weather phenomena that science has not yet fully explained. a quiet mystery that still drifts through the edges of our understanding. Hurricanes are powered entirely by warm ocean water, and the moment they move over land or over cold water, they begin to weaken and die. This makes the ocean both the birthplace and the fuel source of every hurricane that has ever existed. As warm seawater evaporates, it rises into the atmosphere carrying enormous amounts of heat energy. This rising warm air feeds the storm's rotation, keeping the winds spinning and the clouds building. A hurricane crossing warm, open ocean can strengthen rapidly, sometimes doubling its wind speed in just 24 hours, a process called rapid intensification. But when the storm moves over land, it loses access to that warm water. The energy source is cut off, friction from the ground slows the winds, and the storm gradually loses its structure and weakens into ordinary rain and wind. Some hurricanes make landfall at their peak strength, releasing all that stored oceanic energy in one concentrated burst over the coastline. Lightning does not only strike from clouds down to the ground, it can also travel in the opposite direction, from the ground up into the sky. This upward lightning most commonly originates from very tall structures like skyscrapers, communication towers, and wind turbines, which can initiate a lightning strike that travels upward toward the storm cloud above. There is also a group of rare and visually stunning electrical phenomena that reach far above ordinary thunderstorms, up into the upper atmosphere and even the edge of space. These include sprites, faint reddish flashes that appear above storm clouds, and elves, which are brief, expanding rings of light caused by the electromagnetic pulse of a lightning bolt below. For a long time, pilots reported seeing these strange lights above storms, but scientists were skeptical. Today they are well documented and studied, a reminder that the electrical activity of a storm extends much further above and below the visible cloud than most people ever imagine.
Storms have been shaping human history for thousands of years in ways that go far beyond weather. The outcome of battles, the fate of entire naval fleets, and the success or failure of colonial voyages have all been determined by the arrival of unexpected storms. In 1281, a massive typhoon destroyed a Mongol fleet attempting to invade Japan, saving the country from conquest, and leading the Japanese to call this storm the kamikaze, the divine wind. Spanish Armada ships were scattered and sunk by storms off the coast of Scotland and Ireland in 1588, changing the balance of power in Europe. Hurricanes destroyed early colonial settlements in the Caribbean and altered the course of the Atlantic slave trade. Long before humans could predict or understand storms, they worshipped them, feared them, named them after gods, and built entire mythologies around the idea that the sky itself had the power to decide the fate of nations. Elephants, sharks, and several other animals have the remarkable ability to sense a storm approaching long before any human can detect it. Elephants have been observed moving to higher ground hours before a major storm or flood arrives, apparently detecting infrasound, very low-frequency sound waves below the range of human hearing, produced by distant storms. Sharks often dive to deeper, calmer water before a hurricane arrives, responding to the drop in barometric pressure that accompanies the approaching storm. Birds alter their migration routes to avoid storm systems days in advance, navigating around weather that hasn't yet appeared on any forecast. Dogs and cats become restless and anxious before storms, likely sensing changes in static electricity, air pressure, and sound. These animals carry within them ancient sensory systems, fine-tuned over millions of years of evolution, allowing them to read the language of the atmosphere in ways that human technology is only beginning to match. The water cycle is one of the most elegant and continuous processes in all of nature, and storms are one of its most powerful expressions. Water evaporates from the oceans, rivers, and lakes under the warmth of the sun, rising invisibly into the atmosphere as water vapor. As it rises and cools, it condenses around tiny particles of dust and sea salt to form clouds. When enough water collects in a cloud, it falls back to the ground as rain, snow, or hail. Storms accelerate this process dramatically, pulling enormous quantities of water vapor out of the atmosphere and returning it to the ground in hours. A single large hurricane can release more than 2.4 trillion liters of rain in a single day, an almost incomprehensible amount of water. Every raindrop that falls during a storm was once part of the ocean, perhaps floating above a tropical sea just days or weeks before landing quietly on a rooftop, a forest, or a field. The rotation of the Earth has a subtle but powerful influence on the behavior of all large storms. This influence is called the Coriolis effect, named after the French mathematician Gaspard Gustave de Coriolis, who first described it mathematically in the 19th century. Because the Earth is a sphere, rotating from west to east, objects moving freely across its surface, including large bodies of air, appear to curve as they travel. In the northern hemisphere, this curving is to the right. In the southern hemisphere, it is to the left. For storms, this means that the air flowing into a low-pressure system is gradually twisted into a spiral rather than flowing straight inward. This is why all large storm systems, hurricanes, typhoons, and cyclones, have that distinctive rotating, swirling structure when seen from above. Without the Coriolis effect, storms would simply pull air straight inward and collapse quickly. The gentle spin of our planet is what gives storms their shape, their power, and their long, graceful lives.
Storm chasers are scientists, meteorologists, and researchers who do something that most people would consider unthinkable. They drive directly toward dangerous storms instead of away from them. Their goal is to get as close as possible to tornadoes, supercell thunderstorms, and severe weather systems in order to collect data that cannot be gathered any other way. They carry specialized equipment, including weather balloons, radar instruments, and armored vehicles designed to withstand flying debris and extreme winds. The information they gather helps scientists better understand how tornadoes form, how strong they will become, and how long they will last. This research has directly improved tornado warning systems, giving people in the path of the storm more time to find shelter. Storm chasing is genuinely dangerous work. Several chasers have been killed over the years by the very storms they were studying. But the data they collect has saved countless lives, making their quiet courage one of the less celebrated but deeply important contributions to modern weather science. Heavy rain from a powerful storm can transform a calm, shallow river into a raging flood within just a few hours. This process, called flash flooding, is one of the deadliest weather-related hazards in the world. When rain falls faster than the ground can absorb it, the water runs off across the surface, flowing downhill and collecting in streams, rivers, and valleys. In mountainous or canyon areas, this runoff can funnel into narrow channels and build into a wall of rushing water that moves with tremendous force and speed. Flash floods can carry boulders, uproot trees, and sweep away cars and buildings. They often arrive with little warning, and because they can occur far from where the rain is actually falling, people in dry canyons or valleys can be caught completely off guard. More people in the United States die from flash flooding each year than from any other storm-related cause, including tornadoes and lightning. Blizzards are among the most isolating and quietly powerful weather events in nature. Unlike the dramatic violence of a tornado or hurricane, a blizzard works slowly and patiently, covering the world in a deep, thick silence. A true blizzard requires not just heavy snowfall, but also sustained winds of at least 56 kilometers per hour, which whip the snow into dense clouds that reduce visibility to nearly zero. In a full blizzard, a person can become disoriented and lost just a few meters from safety, unable to see anything in any direction. Snowdrifts can build to extraordinary heights, several meters tall in some cases, burying cars, blocking roads, and sealing doors shut from the outside. After the storm passes, the landscape is transformed completely, smoothed and softened under a white blanket that muffles every sound. The world after a blizzard is one of the quietest places in nature. a stillness so complete it feels almost sacred. Lightning plays a quiet but important role in keeping the soil of our planet alive and fertile. When a lightning bolt travels through the atmosphere, the enormous heat and energy it produces breaks apart nitrogen molecules in the air. Ordinary nitrogen gas consists of two nitrogen atoms bonded together so tightly that most living things cannot use it directly. But lightning breaks those bonds, freeing the nitrogen atoms to combine with oxygen and eventually dissolve into the soil with rainfall. Plants can absorb this nitrogen-rich water through their roots and use it to grow. This process, called lightning fixation, contributes a small but meaningful portion of the nitrogen that enters Earth's ecosystems every year. Long before humans invented synthetic fertilizers, lightning was quietly enriching the soil with every storm, feeding the forests and grasslands of the world one bolt at a time. It is a reminder that even the most violent expressions of nature often carry within them something quietly nourishing. Mammatus clouds are one of the most unusual and visually striking things a storm can produce in the sky. While most clouds have flat or rounded bases and build upward, mammatus clouds hang downward from the base of a storm cloud in rounded pouch-like lobes that can stretch across the sky for hundreds of kilometers. Their name comes from the Latin word for breast, describing their distinctive shape. They form when pockets of cold, moist air sink downward from the base of a cumulonimbus cloud, pushing through the drier air below and creating those remarkable hanging shapes. Mammatus clouds are often seen beneath the anvil of a large thunderstorm, and their appearance can indicate that the storm above is particularly severe and energetic. Despite their somewhat ominous appearance, mammatus clouds themselves are not dangerous. They are simply a visual sign of the powerful turbulence happening inside the storm above. People who see them for the first time are often stopped completely still by the strangeness and beauty of the sight. Storms at sea have terrified sailors and shaped maritime history for thousands of years. Before modern weather forecasting existed, a voyage across the open ocean was a journey into genuine uncertainty, where a sudden storm could appear without warning and determine whether a ship and its crew survived or disappeared forever beneath the waves. Ancient sailors developed remarkable skills for reading the sky, the wind, and the behavior of ocean waves to anticipate storms before they arrived. They watched for changes in cloud shape, the direction of swells, the color of the sunset, and the behavior of seabirds. Many of these observations were encoded into rhymes and sayings passed down through generations. Red sky at night, sailor's delight. Red sky in morning, sailor's warning, is one that has been used for centuries and still contains genuine meteorological truth. The relationship between storms and the sea has produced some of the most enduring myths, legends, and literature in all of human culture. The wind inside a powerful tornado behaves in ways that seem almost impossible. Scientists have documented cases where a tornado drove a simple piece of straw completely through a solid wooden fence post, embedding it several centimeters deep in the wood. This happens because the wind is moving so fast that even a lightweight object like straw carries enormous kinetic energy, enough to penetrate surfaces that would normally stop it instantly. The same physics explains why tornado debris causes such devastating injuries and why even small objects become lethal projectiles in extreme winds. A tornado can also create pressure differences so extreme that buildings can appear to explode from the inside, as the low pressure outside causes the higher pressure air inside to push outward through walls and windows. Storm engineers and architects study these effects carefully to design buildings that can better withstand tornado winds, slowly learning from each storm how to build more safely in the places where tornadoes are most likely to return. Every storm, no matter how powerful, is part of a much larger and quieter system that has been operating on Earth for billions of years, the general circulation of the atmosphere. The sun heats the Earth unevenly, warming the equator more than the poles. This temperature difference drives enormous flows of air from warm regions toward cold ones, creating the major wind patterns and weather systems that circle the globe. Storms are concentrated bursts of energy within this larger flow. releasing heat and moisture that has been accumulating in the atmosphere, and returning the atmosphere to a more balanced state. Without storms, heat would build up in the tropics to levels that could not support life as we know it, and the poles would grow colder still. Storms are not interruptions to the normal state of the atmosphere. They are the mechanism by which the atmosphere does its most important work, moving energy and water from where there is too much to where there is too little. Weather satellites orbiting high above the Earth have completely transformed the way humans understand, track, and prepare for storms. Before satellites existed, a hurricane forming in the middle of the ocean might go completely undetected until it was close enough to land for ships or coastal observers to report it. There was no way to see the full shape of a storm system, measure its size, or track its movement across vast stretches of open ocean. The first weather satellite, TIROS-1, was launched in 1960 and sent back the first grainy images of storm systems from space. Today, a network of sophisticated geostationary satellites provides continuous, real-time images of weather systems across the entire planet, updating every few minutes. Meteorologists can track a hurricane from the moment it begins to organize as a cluster of thunderstorms over tropical water, following its every movement and change until it finally dissipates. This technology has saved hundreds of thousands of lives by giving coastal populations days of advance warning before a major storm arrives. Ice crystals inside a storm cloud do something extraordinary that most people never think about. They create electricity through friction in a process that scientists call charge separation. As ice particles of different sizes collide inside the turbulent air of a thunderstorm, the smaller, lighter ice crystals tend to acquire a positive electrical charge and are carried upward by the storm's updrafts. The larger, heavier particles called graupel, soft hail, tend to acquire a negative charge and fall toward the base of the cloud. Over time, this sorting process creates a cloud with a strong positive charge near the top and a strong negative charge near the bottom. The ground below, influenced by the negative charge above, develops a positive charge in response. When the difference in charge between the cloud base and the ground becomes large enough, the electrical barrier of the air between them breaks down and a lightning bolt bridges the gap. The entire thunderstorm is in essence a slow building and then suddenly releasing electrical machine. Storms are not silent events. They produce an enormous range of sounds that stretch far beyond what human ears can detect. Thunder, rain, and wind are the sounds we know well, but storms also generate infrasound, which consists of very low-frequency vibrations that travel through the air and ground over hundreds and even thousands of kilometers. These deep, invisible pulses are too low for humans to hear, but they can be detected by sensitive scientific instruments called infrasound arrays placed around the world. Scientists use these instruments to monitor large storms remotely, tracking their intensity and movement from great distances. Animals that can hear infrasound, like elephants and certain birds, use these signals as an early warning system, sensing the approach of a major storm long before it arrives. A powerful hurricane produces infrasound continuously as it travels across the ocean, broadcasting its presence in a deep, constant voice that the atmosphere carries quietly around the entire planet. Raindrops are not the teardrop shape that most people imagine when they think of falling rain. That familiar pointed top, rounded bottom shape is actually a myth, a picture that has become so common in drawings and symbols that it feels true even though it is not. In reality, small raindrops are almost perfectly spherical, like tiny glass marbles falling through the air. Larger raindrops, however, are flattened on the bottom as air resistance pushes upward against them while they fall. The very largest raindrops become so flattened that they look more like tiny hamburger buns than spheres, with a concave bottom and a rounded top. If a raindrop grows too large, the air resistance and internal instability cause it to break apart into smaller droplets before it reaches the ground. The shape of a raindrop is constantly changing as it falls, wobbling and adjusting in response to the air moving around it, never holding any single shape for more than a fraction of a second. Hurricanes are known by different names depending on where in the world they form, but they are all the same type of storm. a tropical cyclone. In the North Atlantic Ocean and the northeastern Pacific Ocean, they are called hurricanes. In the northwestern Pacific Ocean, the same type of storm is called a typhoon. In the South Pacific and Indian Ocean, it is simply called a cyclone. The word hurricane itself comes from the indigenous Caribbean word huracan, the name given to a god of storms by the Taino people who lived on the islands long before European explorers arrived. The word typhoon likely comes from the Arabic tufan or the Chinese taifeng, both meaning a great wind. Different cultures around the world independently develop names for these terrifying storms, each name carrying within it a long history of fear, respect, and the very human need to give a name to the forces that shape our lives and our landscapes. Cumulonimbus clouds, the tall, dark towers that produce thunderstorms, are the most powerful and energetic clouds in Earth's atmosphere. A single large cumulonimbus cloud can contain up to 500,000 tons of water in the form of droplets and ice crystals, all suspended in the air by the powerful updrafts moving through the cloud. Inside this cloud, air can be moving upward at speeds of over 160 kilometers per hour in the strongest updrafts, fast enough to keep large hailstones airborne for extended periods. The cloud generates its own weather system, with winds, precipitation, and electrical activity all happening simultaneously within its boundaries. From outside, a mature cumulonimbus looks like a massive dark tower with a bright, flat anvil spreading across the top. From inside an aircraft, flying through one is considered extremely dangerous, with violent turbulence, icing, and lightning making it one of the most hostile environments in the lower atmosphere. Pilots carefully navigate around them, giving these enormous clouds the wide respect they deserve. Dry thunderstorms produce some of the most dangerous conditions that firefighters face anywhere in the world. When lightning strikes dry vegetation without any accompanying rainfall to dampen the ground, fires can ignite across vast areas almost simultaneously. A single dry thunderstorm moving across a dry forest or grassland can start dozens of fires in a matter of hours, each one beginning as a small smoldering spot where a lightning bolt touched the earth. In hot, dry conditions with strong winds, which are often present during and after a storm, these small ignitions can grow with terrifying speed. The 2020 wildfire season in California was partly driven by a series of dry lightning storms that struck the state during a period of extreme heat, sparking thousands of fires across millions of acres of dry landscape. Fire agencies in regions prone to dry thunderstorms monitor lightning strike data in real time during storm season, sending crews to investigate every recorded strike in remote areas before a small spark becomes an uncontrollable blaze. Storm surges are the most deadly aspect of a hurricane, and understanding them requires imagining the ocean being physically pushed by the wind for hundreds of kilometers before piling up against a coastline. As a hurricane moves across the ocean, its powerful circular winds drag the surface water along with them. On the right side of the storm in the northern hemisphere, where the wind direction and the storm's forward motion combine, this effect is strongest. The water has nowhere to go as it approaches the shallowing coastal seafloor, so it rises. The lower atmospheric pressure at the storm's center also allows the sea surface to dome upward by half a meter or more. The combined result can raise coastal sea levels by many meters in just a few hours. In 1970, a cyclone striking Bangladesh produced a storm surge that killed an estimated 500,000 people in a single night, one of the deadliest natural disasters ever recorded. Today, evacuation planning in coastal areas is built almost entirely around the threat of storm surge rather than wind alone. Storms help regulate the temperature of the entire planet by acting as giant heat transfer engines, moving warmth from the tropics toward the cooler regions closer to the poles. The tropics receive far more solar energy than they radiate back into space, so without some mechanism to move that excess heat away, the equatorial regions would grow hotter and hotter over time. Hurricanes are particularly efficient at this task. A single large hurricane can transport enormous quantities of heat energy northward or southward in just a few days. Thunderstorms perform the same function on a smaller scale, lifting warm, moist air from the ground up into the upper atmosphere, where it spreads outward and travels toward higher latitudes. This constant redistribution of heat is what makes Earth's climate livable across such a wide range of latitudes. Storms are not simply destructive events. They are essential components of the planetary thermostat that has kept Earth's temperature within the range needed for life for billions of years. Some tornadoes are completely transparent and invisible when they first form. A tornado is made of rapidly spinning air, and air itself is invisible. What makes a tornado visible is the debris it picks up from the ground: dust, soil, leaves, and broken objects, and the condensation funnel that forms when the low pressure inside the tornado causes water vapor to condense into tiny droplets. When a tornado forms over very clean, dry pavement or open water, and the air is relatively dry, there may be no visible funnel and very little debris cloud at first. In these cases, the tornado can be upon a person before they even realize it is there. Storm chasers have instruments that can detect the rotation of an invisible tornado through Doppler radar, which measures wind speed and direction by analyzing how radio waves bounce back from rain and debris. This technology has made it possible to issue warnings for tornadoes that cannot yet be seen, giving people vital extra minutes to find safety. The water that falls as rain during a storm has an ancient and remarkable history. Every water molecule on Earth has been cycling through the environment for billions of years, evaporating from the oceans, rising into clouds, falling as rain, flowing into rivers, soaking into the ground, and returning eventually to the sea. The water in a raindrop falling on your hand today may have once flowed through a river in ancient Mesopotamia, fallen as snow on a glacier that no longer exists, or been part of the ocean that surrounded the first single-celled life forms on Earth. Water molecules are extraordinarily durable. They are not destroyed or created by the water cycle, only moved from place to place. A storm is one of the most powerful steps in this ancient journey, gathering water from a vast area of ocean or land and concentrating it into a brief, intense rainfall that sends those ancient molecules on the next stage of their endless travels. The stillness that follows a storm is one of the most peaceful experiences in nature, and it has a quality that is different from ordinary quiet. After the wind has stopped and the last drops of rain have fallen, the air is washed clean of dust, pollen, and pollution. The sky often clears to a deep, vivid blue as the storm carries away the haze that had been building for days. The ground is wet and dark, releasing the warm, earthy scent of petrichor into the cool, ozone-touched air. Birds begin to call again from the trees. The leaves on every tree are clean and bright. There is a sense of something having passed, of a great energy having moved through and gone, leaving everything behind it refreshed and strangely new. This quality of after-storm stillness has inspired poets, composers, and painters for centuries. It is a moment that the natural world offers freely and often, a quiet, generous reminder that even the most turbulent things eventually find their way to calm. Storms have been part of Earth's story for an almost incomprehensible length of time. Long before any plant, animal, or living creature existed on this planet, storms were already forming over the young oceans and bare rocky continents. In Earth's earliest atmosphere, billions of years ago, the air was thick with water vapor, carbon dioxide, and other gases, and the energy from the young sun was already driving the same basic processes of evaporation, cloud formation, and rainfall that we see today. Some scientists believe that the constant lightning of those ancient storms may have played a role in creating the first complex molecules that eventually led to life itself, sparking chemical reactions in pools of warm water along the shoreline. Every storm that passes over you today is part of an unbroken chain of storms reaching back to the very beginning of our planet, a continuous process that has never once paused in 4.5 billion years of Earth's history. Every raindrop that falls during a storm carries within it a small piece of the ocean's history. Water evaporates from the surface of the sea when sunlight warms it, rising invisibly into the air as water vapor and leaving the salt behind. This pure, fresh water vapor travels with the wind, sometimes for thousands of kilometers, before it cools, condenses around tiny particles of dust or sea salt, and forms the droplets that eventually fall as rain. A single raindrop may have evaporated from the Pacific Ocean, traveled across a continent on the upper winds, and fallen weeks later onto a quiet garden or forest far inland. The water cycle connects every ocean, river, cloud, and raindrop into one continuous flowing system that has no beginning and no end. When rain touches your skin during a storm, you are feeling water that has journeyed across unimaginable distances, drawn upward by the sun, and returned by the patient, quiet work of clouds. After a storm passes and the air begins to clear, the world smells different in a way that almost everyone recognizes, but few people can explain. That clean, sharp, refreshing scent comes from several sources working together. Ozone, produced by lightning breaking apart oxygen molecules in the air, gives a faint electrical sharpness to the smell. Petrichor, released when raindrops strike dry soil, carries a warm and earthy richness that rises from the ground in little invisible clouds. Plants release chemical compounds after rainfall, and the air itself carries the cool, neutral scent of clean, washed air, free from the dust and pollen that had accumulated over days. Together, these scents create something that feels deeply familiar and deeply comforting, a sensory signal that the storm has passed and the air is clean and safe. It is a smell that connects us to every human being who ever stood in a doorway after a storm and breathed in the quiet, renewed world outside. Storms help move heat from the warm tropics toward the cooler parts of the planet in a process that has been balancing Earth's temperature for billions of years. The equator receives more energy from the sun than it can radiate back into space, and without some mechanism to move that excess warmth, the tropics would become unbearably hot, while the poles grew ever colder. Storms are one of the primary tools the atmosphere uses to solve this problem. A hurricane spinning northward across the Atlantic carries enormous quantities of warm tropical air and warm ocean heat with it, releasing that energy gradually into higher latitudes as it weakens. Thunderstorms lift warm surface air high into the atmosphere, where it spreads outward toward the poles. Over millions of years, this constant redistribution of heat has maintained the relatively stable climate that allowed complex life to evolve and thrive across the planet. Every storm, even the most destructive one, is quietly doing this essential balancing work. The wind in a storm is one of the simplest things in nature to explain and one of the most powerful things to experience. Wind is simply air moving from an area of high pressure to an area of low pressure, following the same basic principle as water flowing downhill. Inside a storm, the low-pressure center acts like a drain, pulling air inward from all directions. The greater the difference in pressure between the center and the surrounding air, the faster the wind flows. In an ordinary thunderstorm, this pressure difference might produce winds of 60 or 70 kilometers per hour. In a major hurricane with an extremely deep low-pressure center, the same principle produces winds of 250 kilometers per hour or more. The atmosphere is always trying to equalize pressure across the planet's surface, and wind is the mechanism it uses to do so. Every breeze, gust, and hurricane is the atmosphere trying patiently and continuously to find its balance. A gentle rain shower and a violent hurricane are part of exactly the same process. The continuous cycle of water moving between the ocean, the atmosphere, and the land. The difference between them is only one of scale and energy. Both begin with evaporation from a water surface. Both involve water vapor condensing into clouds, and both return water to the earth as precipitation. A light drizzle on a spring afternoon and a tropical cyclone carrying trillions of liters of water across an ocean are expressions of the same fundamental mechanism, driven by the same sun, following the same physical laws. Nature does not distinguish between them. They are simply different points on a continuous spectrum of atmospheric activity. This connection between the gentle and the powerful is one of the most calming and beautiful things about storms. Even the most fearsome hurricane is at its heart just rain doing what rain has always done. Storms are one of nature's most efficient ways of releasing energy that has been accumulating slowly and invisibly in the atmosphere over many days. As the sun heats the ocean and the land, water evaporates and warm air rises, storing enormous amounts of energy in the form of heat and moisture. This stored energy builds gradually, day by day, until the atmosphere becomes unstable enough for a storm to form. The storm then acts like a release valve, converting all that stored energy into wind, rain, lightning, and thunder in a matter of hours. After the storm passes, the atmosphere is more stable, temperatures have moderated, and the energy balance has been partially restored. It is a rhythm that the atmosphere has been following for billions of years. Slow accumulation followed by sudden release, building and releasing, as naturally and inevitably as breathing. Storms are not accidents or disruptions. They are the atmosphere doing exactly what it is designed to do. Lightning connects the sky and the ground in one of the most dramatic moments in all of nature, completing an electrical circuit between the cloud and the earth in a fraction of a second. In that brief instant, hundreds of millions of volts of electrical potential are discharged, heating the surrounding air to temperatures hotter than the surface of the sun. The light from a lightning bolt travels to our eyes almost instantaneously, which is why we see the flash before we hear the thunder. The bolt itself follows a path called a stepped leader, an invisible channel of ionized air that the lightning carves downward from the cloud in a series of tiny steps, each one choosing the path of least electrical resistance through the air. When the stepped leader gets close enough to the ground, an upward streamer of positive charge rises to meet it, and when the two connect, the main lightning bolt surges back upward through the channel in a return stroke so bright it illuminates the entire sky. The water cycle means that every storm is intimately connected to every other storm that has ever occurred on Earth. The rain that falls today evaporates tomorrow, rises into a new cloud, and falls again somewhere else as part of a new storm. Water molecules cycle through the atmosphere continuously, and the same molecules that were in a medieval rainstorm over Europe may be in a cloud forming over the Pacific Ocean today. Storms are not isolated events. They are individual expressions of a single, continuous planetary process that has never stopped. When a storm passes over a city, a forest, or an ocean, it is not creating something new, so much as it is continuing something ancient. It is the same water, the same sun, the same atmospheric physics that has been driving rain and storms across this planet since long before any living thing existed to watch the lightning flash or listen to the thunder roll across the quiet, darkening sky. Somewhere on Earth right now, at this very moment, a storm is quietly beginning to form. Over warm tropical waters, a cluster of thunderstorms is organizing itself, drawing energy upward from the sea. Over a sun-heated plain, warm air is rising rapidly toward a gathering bank of dark clouds. Over a mountain range, moist air is being pushed upward until it cools and condenses into a thick, gray mass. Most of these beginnings will come to nothing. The storms will form, produce some rain, and perhaps a little lightning, and then fade quietly away without ever reaching their full potential. But some will grow. Some will strengthen over days, drawing more and more energy from the warm ocean below, spinning slowly into great spiraling systems that will eventually make landfall and release all their stored power onto the shore. The Earth is always in the process of making storms, always building and releasing, always in motion. Snow that falls during a blizzard is made of millions of individual ice crystals, and no two of them are exactly alike. Each snowflake begins as a tiny particle of dust or pollen, floating high in a cold cloud, around which water vapor slowly freezes into a six-sided crystal. As the crystal falls through layers of air with different temperatures and humidity levels, it grows in a unique pattern determined by the exact conditions it encounters along the way. The six-sided symmetry of every snowflake comes from the molecular structure of water itself. The way water molecules bond together at specific angles when they freeze always produces that characteristic hexagonal shape. A blizzard carrying billions of these crystals transforms the world beneath it into a place of deep, soft silence, covering every surface in a white layer that absorbs sound and softens every edge and outline. The violence of the wind above and the delicate perfection of each individual crystal below exist at the same moment, together, inside the same storm. A storm cloud floating in the sky contains an almost unbelievable amount of water. A large cumulonimbus thunderstorm cloud can hold up to 500,000 metric tons of water in the form of tiny droplets and ice crystals suspended in the air by powerful updrafts. That is the equivalent of hundreds of thousands of fully loaded trucks worth of water, all floating effortlessly above the ground. The cloud appears to float because the water droplets inside it are so incredibly small and light that the gentle upward movement of air inside the cloud is enough to keep them aloft. Only when these droplets combine and grow heavy enough to overcome the updrafts do they begin to fall as rain. It seems almost impossible that something so heavy could hang so quietly in the sky, drifting slowly overhead while the ground below goes about its ordinary business, unaware of the enormous weight of water suspended just above it in the peaceful-looking cloud. Rain falls at different speeds depending on the size of the drops, and the range is wider than most people realize. The finest, lightest drizzle falls at only about 1 meter per second, drifting down so gently that it barely seems to fall at all, hanging in the air like a soft mist. Medium-sized raindrops fall at around 6 or 7 meters per second. The largest raindrops, just before they become too large and break apart, fall at close to 9 meters per second. All of these drops reach what is called terminal velocity, the speed at which the drag from the air exactly balances the pull of gravity. So the drop falls at a constant speed rather than accelerating all the way to the ground. If raindrops continue to accelerate like falling stones, even a gentle rain shower would sting painfully on bare skin. Instead, the air acts as a gentle brake, slowing each drop to a speed that feels like nothing more than a quiet, steady tapping on the leaves and rooftops below. Storms can create what scientists call atmospheric rivers, long, narrow corridors of concentrated water vapor that flow through the sky like invisible rivers thousands of kilometers long. These rivers of moisture in the atmosphere can carry as much water as 10 to 15 times the flow of the Mississippi River, all moving through the air in a stream that may be only a few hundred kilometers wide, but stretches for thousands of kilometers across an ocean. When an atmospheric river makes landfall and is forced upward by mountains or other terrain, it can release enormous amounts of rain in a very short time, causing major flooding and dramatically replenishing reservoirs and snowpacks. The western coast of North America, the British Isles, and parts of Norway experience some of the most powerful atmospheric rivers on Earth. They are not visible from the ground, these great rivers flowing silently overhead, but when they arrive and begin to rain, their presence becomes immediately and powerfully clear. The water falling in a storm today is the same water that has been cycling through Earth's atmosphere since the planet formed. Water molecules are essentially indestructible under normal conditions on Earth. They are not created or destroyed, only moved endlessly from one place to another. The water cycle has been running continuously for over 4 billion years, and every drop of rain that falls anywhere on Earth is part of this ancient, unbroken journey. Some of the water molecules falling in today's storms may have once been locked inside a glacier that melted millions of years ago, or flowed in a river through a landscape that no longer exists, or fallen as rain on forests that have long since turned to coal deep underground. Each raindrop is a traveler with an ancient history, arriving quietly from somewhere unimaginably distant in time, resting briefly on the ground, and then rising again to continue its endless journey through the sky. Somewhere on Earth at this very moment, a storm is fading and coming to its end. The winds are dropping, the clouds are thinning, the lightning has stopped, and the last drops of rain are falling from a sky that is slowly beginning to lighten at the edges. Every storm, no matter how powerful or how long it has lasted, eventually reaches the point where its energy is spent and its moisture is exhausted. The warmth that fueled it has been released. The water it carried has been returned to the ground. The electrical charges it accumulated have been discharged. What remains is a quieter sky, a cleaner atmosphere, and a landscape that has been changed, however slightly, by the passing of the storm. This ending is not a defeat. It is the completion of something. The storm has done its work. moved its energy, delivered its water, and fulfilled its purpose. Now it rests, dissolving gently back into the ordinary sky from which it came. Clouds never look exactly the same twice. They are constantly reshaping themselves, growing and shrinking, thickening and thinning, as the temperature, humidity, and wind conditions around them change from moment to moment. A cloud that looked like a gentle white mass at sunrise may have grown into a dark, towering thunderstorm by afternoon, and by evening may have spread out into a thin, wispy layer, barely visible against the darkening sky. Storm clouds in particular are constantly in motion, with new towers forming along their edges while older parts evaporate and disappear. From the ground, watching the clouds build before a storm is one of the most quietly dramatic experiences that nature offers freely to anyone who takes a moment to look up. The sky is never still, never finished, never the same as it was a minute ago. It is always in the process of becoming something new, driven by the same invisible forces of heat, moisture, and pressure that have shaped every storm that has ever formed on this planet. Every storm, no matter how fierce, eventually grows quiet and fades. A hurricane that spent days tearing across the ocean arrives at land and weakens within hours, its energy dissipating as it loses contact with the warm water that sustained it. A tornado that seemed unstoppable lifts back into the cloud as quickly as it descended, leaving behind a strip of changed landscape and then vanishing completely. A thunderstorm that lit up the sky for hours gradually loses its updrafts. Its lightning becomes less frequent, its thunder grows more distant, and eventually the rain softens to a drizzle and then stops altogether. There is something deeply reassuring about this quality of storms. Their inevitability, yes, but also their finitude. They arrive with tremendous energy and they leave with none. They are complete in themselves, with a beginning, a middle, and an end. And when they are gone, the sky they leave behind is often the clearest, deepest, most beautiful sky of all. The earth is always in motion, always breathing, always moving energy and water from one place to another in a process that never stops and never sleeps. Storms are the most visible and dramatic part of this process. The moments when the slow, invisible work of the atmosphere becomes something you can see, hear, and feel. But between the storms, the same work continues quietly. Water evaporating from the ocean surface in the steady sunshine, rising invisibly into the atmosphere, drifting on the upper winds across continents and seas, slowly gathering into clouds, waiting patiently for the conditions that will allow it to fall again. The atmosphere is never truly at rest. It is always preparing the next storm, always building the energy and moisture that will eventually release itself in lightning and rain and wind. The quiet days between storms are not pauses in the story. They are the story continuing, chapter after chapter, in the same patient, tireless voice. Storms remind us, gently and powerfully, that the earth is alive in the deepest sense of the word. It breathes through its winds, circulates warmth through its ocean currents, and releases energy through its storms the way a living body releases heat. Every cloud that forms above an ocean, every bolt of lightning that connects the sky to the ground, every raindrop that falls on a quiet forest is part of this vast, living system that has been sustaining itself for billions of years without pause. We live inside this system, not above it or outside it. The same water that falls in tonight's storm will one day evaporate from a lake near your home and rise into a new cloud. The same winds that carry hurricanes across the ocean also carry the seeds of trees and the songs of migrating birds. We are woven into this system completely and inescapably, and storms are simply the moments when we feel that connection most clearly, most deeply, and most unmistakably.